here is the static image. The feed material, so this is liquid containing curd particles, is pumped in here at the right-hand side. And then it's pumped into a rotating bowl. So this wall here on the outside is a rotating bowl. And it's rotating at a very high speed. And that creates the centrifugal force. That creates the conditions that separate the solids from the liquid. So what happens is the solid particles are thrown to the outside of the bowl. So they're thrown to the wall, the rotating wall. And then they're augured back in this direction from left to right. So they're thrown to the wall and they create a cake on the surface of the wall. And then this auger screw transports the solid particles towards an outlet at this point. And then we have removal of the solid particles at this point. This is our casein particles. Now the liquid is removed at a different point in the centrifuge. So if we were to look at this at a different angle, what we would see is this is our wall and it's rotating. And on the outside of our wall, we have our casein particles and they form the layer. So this is our casein particles and they've been thrown to the outside of the wall due to the centrifugal force. The liquid is inside of that layer. So we have concentric layers. We have our wall on the outside, we have our casein layer inside that, and then we have our liquid layer. So this is our liquid layer in here. And inside in the centrifuge, there's separate channels which that liquid is diverted to. So the liquid is transported in channels toward the opposite end of the centrifuge. So this is our whey here, for example, in our first centrifuge in the process. So we have whey being removed in one direction and curd particles being removed in another direction. If we have very small particles present, they might be removed in this whey fraction. They might be too small to be thrown against the internal walls of the centrifuge. So this is a decanter centrifuge, and it's used in any operation where you want to separate a large mass of solid particles from liquid. So it's used in the separation of casein from whey, solid casein from whey, but it's also used in the separation of crystals from liquids. So later when we're talking about lactose manufacture, we'll see the exact same decanter centrifuge being used. So these are some additional notes about the decanter centrifuge that you can have a look at. It's actually, like many pieces of equipment, once you start reading about it, it gets very confusing because there's a special language. Okay? So if you start looking at this, you will see words like cloud, beach, baffles, dam plates. So there's lots of different terminology here being used, and I do not need you to know that terminology. Okay? You just need to know it's a centrifuge. It operates according to Stokes' law. We're trying to separate two different phases that have a difference in density. We're trying to promote the presence of large curd particles, and the decanter centrifuge is used for that purpose. So when we were talking about spray drying, and when you were talking about it with Urio, you would have seen that the atomization process works by forcing a liquid through a very, very narrow orifice under high pressures. And that works very well if we're dealing with a liquid. But as you can imagine, if you're trying to pump a slurry containing very large casein particles through one of those very narrow orifices, you might have some problems. Okay? So it doesn't work. You can't use a spray dryer for this type of system. So instead you use dryers like attrition dryers or ring dryers. And these operate based on somewhat different principles compared to the spray dryer. So this is an example of an attrition dryer. And it looks quite complicated, but for our purposes, it's quite simple. And it does two things simultaneously. It mills the casein curd, and it also dries the casein curd particles. So the slurry of casein enters in this inlet here at the bottom of the attrition dryer. And at the same time, there's hot, dry air pumped into the main chamber in the attrition dryer. And inside in the attrition dryer, you have a series of rotors, okay? So these effectively function as agitators, but what they are is a complex network of blades. So the slurry enters here, and you have this complex network of blades rotating very rapidly. And at the start of the drying process, you've got these very widely spaced blades. So this breaks very large chunks of curd. So chunks of curd that could be several centimeters large in size. It breaks them down into smaller millimeter-sized particles. And those millimeter-sized particles then are transported through a narrower series of blades, and this breaks the particle size down even further. So the particle size is being broken down, the surface area is increasing, and at the same time, we've got dry air being pumped or flown through the drying chamber. So as the particle size is being reduced, we also have moisture evaporating from the surface of the particles. And this drying process only works effectively if we have a good reduction in particle size. So the particle size needs to be reduced by the milling operation in order for the drying to happen successfully. So this dual functionality, the milling and the drying, is designed to increase the efficiency of the drying, but it's also designed to prevent a defect known as case hardening. So if you have a very large casein particle, and if you expose it to heat in the environment, what can happen is that you have a very effective rate of drying at the surface of the particle. So a case, a hard, solid, dry case, can form at the outside of the particle. But inside in the particle, we can have a very high water content. So if we don't reduce the size of the particles in the dryer, we can have this effect known as case hardening. So instead of drying the entire particle, we only dry the outside, okay? Can anyone think of a problem with that? Why would we care that this case hardening effect happened? Why would that matter? This is a major concern of people who produce things like acid casing. So you're saying if it's harder on the outside, it won't solubilize when someone's making sodium casing, for example, in alkali. Probably, so it would affect functionality. What else might it affect? Huh? Lot heavier, yeah. So remember, when you're talking about powders, one of the advantages of taking out water is that you're reducing its weight. So the shipments of this powder will be much heavier. And you were saying?
It's kind of the same thing, just you have more product than you do.
Yeah, exactly. You're producing more water than protein on a weight basis. Any other problems? Water activity.
Chemical reaction.
That from another room?
You don't think so?
Sounds much funner than this room. Water activity, so that's really important. So we're trying to reduce the water content and by extension the water activity. Why is that important? Shelf life. Why would the shelf life be affected if there's a high water activity? Microbial growth. So we have a particle here that's full of water. And all the things you're saying are true. We could have microbial growth, we could have a heavier material, we could have yields being affected. All of those are true. So we're not really drying the product, we're just drying a small part of it. And as a result, as soon as the product even goes to a quality lab, they'll know immediately the water content is out of spec, the water activity is out of spec, the shelf life is not good. Now, if it doesn't go through a quality lab for some reason, and if it goes out to a consumer or a client, it could lead to disastrous consequences. Because there could be microbial growth where people didn't expect microbial growth because they were expecting a 24-month shelf life when in fact it had a 4-month shelf life, something like that. All of this is to say that the attrition dryer, this technology is very important. It's designed for a specific reason. We have milling and drying happening in the dryer. This promotes a reduction in particle size and efficient drying of the curd particles so that we don't have those problems. Is it done under vacuum?
Yeah.
Let's look. I didn't think so. I didn't think so. I can check. I'll get back to you. Why are you asking that?
I was just wondering what kind of temperature you would need for like the water.
Drying the water? That's a good question. If it isn't in the slides, I'll follow up. Thanks, man. So here we have some more diagrams where you can actually see the blades when the equipment is opened up. And here we have a larger diagram showing some of the ducts through which the air and the vapor is transported after the drying process. Now there is an alternative to attrition drying, and the alternative to an attrition dryer is called a ring dryer. And here are some examples of ring dryers in actual use, and we see that the shape is this kind of looping, large looping kind of structure. So a ring dryer looks very different from an attrition dryer, but in many ways they're similar. So they both have, again, this dual functionality, the milling and the drying. So in this case, we have a product here, so this is our casein slurry, and it's being mixed, and then it's fed by a screw, an auger screw, into something called a disintegrator. Okay? And this here acts as our mill in this process. So inside in this disintegrator, we have a series of blades rotating, which break up the curd particles. So here we have our curd particles, and they've been created in our disintegrator. And here we have hot air being generated, and the hot air is pumped into the disintegrator.